Sometimes I'm using blank. It was actually really good. I was
Okay, so we should be close to the end of chapter 8, if not at the end. We don't have that much left. Okay, which set of reagents is the best choice for this reaction? Okay. Oh, 7. Make a choice. We'll talk about it afterwards. Okay, we're all up there? Okay, so tell me what happened in the reaction. What did we do to the double bond? We added an H and an OH. Agree? Okay. Does A add an H and an OH? Yeah, it does, doesn't it? But what else happens? It rearranges. So A is not the answer. What happens with B? What does B do? It adds an H and an OH, right? But which way? Anti-Markovnikov. Okay, we want to add it Markovnikov, and we want no rearrangement. Which one is it? What does C make?
The triangle.
Yeah, and a epoxide. The triangle. That works. That works. You knew it wasn't C, right? Yeah. Okay. So to open epoxides, which is the triangle, okay, with acid, when there's acid present, the first thing that will happen is you will protonate the O of the epoxide, and then water will attack to open the ring from the opposite side. It's just like when we had a bromonium ion. It was plus on that Br, and so our water's coming in from the opposite side to open it up. The resulting protonated diol is deprotonated with water, which regenerates the acid. So it's typically referred to as acid catalyzed because you regenerated the acid. All right, so here's a ring, okay, and it is getting protonated. They kind of were a little chintzy on their deal. Probably should have redrawn the whole thing. Okay, so this goes there, and that goes to the O. Okay, then the water comes in from the bottom. So if this is sitting up, the water is going to come in from the bottom. It's going to open to the top. So notice that your two OHs are going to be on opposite sides. Okay, this isn't drawn the best, I must say. So here's what I'll do. Maybe I'll make this a wedge, and this a slash, this a slash, this a wedge. Sigh. It's like it's just off enough that It irritates me because I can't draw right. Okay, and then another water molecule will remove the proton, so you end up with a diol. And the key there is to recognize that you always get trans. You always get trans. Okay, your OHs are always going to be on opposite sides. That really is important with the rings, but it's also important with the straight chains because you would get different diastereomers, whether they added on the same side or opposite side, right? Remember those? Okay. All right, so here is a little video, okay? And first I want you to tell me what you think the product of the reaction, okay? So what should happen first? What do you think is going to happen first? And then I'll go find the video. There's my lone pairs. See, the thing is like, oh. All right, so what happens first? We protonate. Okay, why is that always first? If there's acid in there, that transferring of a proton is the fastest thing that can occur. And so if there's an acid in there, you will protonate first. Okay, so you keep that under your hat as a nice little rule of thumb. Okay, so at that point, after we protonated, okay, it'll look like this. Then what do you think is going to happen? Nope, not water. Why isn't it water? What is this? Methanol. Yes, it can function as a base, but that just gets you back to the beginning. Okay, so every little step is typically equilibrium. All right, so what else can it do besides removing the proton and going back to the starting material? What? It can function as a nucleophile. No, it's too weak to be the acid. This is the acid. Okay, so where are we going to go? We have a choice, don't we? We can go the left carbon or the right carbon of the epoxide. Which one are we going to pick? More highly substituted or less highly substituted? More. Why? Because that helps stabilize the positive charge. So where am I going to go now? To the left one or the right one? To the left one, and that's going to open. Okay, and you're going to come in from the bottom and open it to the top, opposite sides. Okay, then what will happen? You have to deprotonate, yes. And another methanol will probably do that. So the product that you should get is going to be this. Okay. All right, so let me show you on the video. Oh, sorry. I got to move this little screen out way. It's black. Okay, which one says acid? One is A, one is base. Okay, so I'm going to hit play. And so the first thing that's going to happen is the acid is going to come in to the view, and we're going to protonate that O. Okay, then methanol adds from the opposite side, and then it's deprotonated. Okay, this little thing is kind of blocky. Can I move that? Oh, I can. Okay, so we're protonating. Methanol's coming in and opening the epoxide, and then deprotonating with another methanol. That's how you get the CH3OH2+ that they used at the beginning. You can use that. You could use sulfuric acid if you want to break it out. It doesn't really matter. They're all 6 of one, half a dozen of the other. You got it? Always remember, more highly substituted carbon and opposite sides. Okay. here. Let's see. Okay, synthesis of syndials. You react alkenes with one of these reagents, okay? Either OSO4 with hydrogen peroxide or cold KMnO4 with OH minus. Okay, so what is OS? Does anyone know what OS is? Osmium. And that compound is called osmium tetroxide. Okay? It's a weird compound. I've never worked with it. And you have to have hydrogen peroxide in there. The other option is to use potassium permanganate, which is purple, and it needs to be basic in order for it to work. And what happens is you make your OHs on the same side. Okay? If you do it with making the epoxide an opening, your OHs are always going to be on the opposite side. Okay, so when you do the osmium tetroxide, why do the OHs end up on the same side? That's because the O's come from the osmium tetroxide. Okay, and so they add from the same side to give you a little 5-membered ring with OS in it, and then the H2O2 breaks it off. Okay, we're not going to worry about the mechanism for that. Okay, so that's you make the cis compound. The OHs are on the same side. Okay, the osmium tetroxide gets reformed, and that is much more inorganic than organic, which is why we're not going to worry about it. Okay, what about KMnO4? It's basically the same thing. You have your permanganate anion, adds to the double bond from the same side, you get the cis glycol. Now, it's really important when you do this one that it is cold. Okay, you have to keep it cold. A lot of times they will say cold on the arrows. Okay, because that's going to make a difference. Now, you could use either one. If I said this going to making the cis dial, which one would you use? You could use either one. Okay, which one would you use? Well, you would use the one that you have probably. The osmium stuff is supposed to be very toxic. Like I said, I've never worked with that. I've worked with permanganate, but permanganate is cheaper and more widely found, and it might be on the shelf in your lab. And so you probably use that first. If it didn't work real well, then you'd worry about the osmium stuff. Okay. Sometimes it's trial and error. Okay, so which reagent would give you the best? Which one is the best for the transformation below? So which reagent should you use for that? Okay. All right, so what would you get for answer A if that was the reagents plus that starting material? What would you get? What does that make? They all make some. Every one of them, A, B, C, D. Yes, you would have one OH on one side, and then the OH on the other side would be opposite. Okay, that's A. What does B give you? The OHs are on the same side. Isn't that what we want? Okay, So the answer is B. What would C give you? What would C give you? What does water and H2SO4 do? Adds a what? I decided this is too big. Yeah. What does water and H2SO4 do? Adds an H and an OH, and how does it add? Mark, how many have? No, there is no sister train. Because you have a carbocation, so it's flat. You get both. Get the OH on both sides. So you would get both enantiomers, even though this one doesn't have an enantiomer. Okay, what about D? What do you get from this one? There's your clue. What? Antimarkovnica. So what does that mean? One carbon gets the H and one gets the OH. Which one? This one gets the H, and this one gets the OH. Okay, what can you tell me about cis and trans? And same side and opposite side. What kind of addition was it besides antimarkovnica? It was also. So what adds from the same side? The H and the OH. So that means that this and this are on the same side, and the methyl is on the other side. Okay, so not only is it antimarkovnica, but it is syn addition. When you have a ring, it's going to make a difference. Okay, all right, help a little review there. Okay, so if you take potassium permanganate and you add it and it's warm, okay, and concentrated, typically they make strong solutions when they do that, the glycol gets formed. Remember, the glycol means the two OHs are on adjacent carbons. The glycol gets formed, but then it gets broken, okay? And you cleave the carbon-carbon bond between those two carbons. Okay, so here is our double bond down here. And we're going to make the glycol, but because it's warm, typically, and concentrated, you might like warm it. You don't even have to necessarily reflux it. You just have to warm it up a little bit. And it will break into pieces. Okay, and notice that it's breaking right here. Okay, this carbon is this one, and this carbon is this one. Okay, so what do you make? You make carbonyl compounds. You're going to get two pieces out of this molecule because we're cleaving it right here. Okay, so a disubstituted carbon, that means that the double bond carbon has two R groups on it, gives you a ketone. If you have a monosubstituted carbon, one R and an H, you get a carboxylic acid. What if you have two H's? You get carbon dioxide, which would bubble up. Okay, be easy to clean that one up. Okay, so let's look at some examples. So look at this one. Okay, notice it says warm concentrated on your arrow. Okay, you'll typically see that. Okay, so we're going to take this and we're going to cleave it. Where are we going to cut the molecule? At the what? At the double bond. Okay, so what do we get from the left side of the double bond? I have a cyclohexane, right? Does this carbon have, this one right here, does it have one R group, two R group, or two R groups, or no R groups? 0, 1, or 2 are your only options. It has two R groups, right? There's a carbon here and a carbon here. Okay, so what do I get? What kind of compound is that? A ketone. Okay, what do I get from the other carbon on the other side? That would be this one. How many R groups does that one have? 1. So what am I going to get? Okay, so it has 1, 2, 3, 4 carbons. 1, 2, 3, 4. And then this is going to become an OH. It actually becomes an aldehyde first, and then it gets oxidized further to the carbon. All right, so here's the actual picture of it. Drawn out vaguely nicely. Okay, now what do you think about that bottom one? How many double bonds do I have? 2. So guess what? It's going to get cut in 2 places. So we're going to cut it here, and we're going to cut it here. Okay? So take each carbon in turn and figure out what you get. So this carbon here has how many H's on it? It has 2 H's, right? So you get a CO2. Carbon dioxide bubbles off. It's hard to catch that, but you could catch it. There's ways to catch carbon dioxide. All right, what about this carbon here? What am I going to get from that one? How many R groups are on that carbon? 2. So basically you're cutting it and you're putting a carbonyl there. Cutting it, putting a carbon. Okay. All right, so that will be, let me see. Yeah, see, it's like not connecting, even though, because I'm like off just enough to drive me crazy. Okay, so this one, so I tried to make it match, okay? So this here is your carbonyl. Okay, so I've got CO2 in that carbonyl. Now, what about this carbon right here, the red dot carbon? What am I going to get from that? How many R groups are on this carbon? 0, 1, or 2? How many R groups? 1. This one. Okay, there's a C attached to it and an H. So there's only 1. It's only monosubstitute. So what do I get here? A carboxylic acid. Okay, what about this carbon up here? I'll make it the triangle carbon. Okay, what do I get from that one? How many R groups are on there? 1. So this carbon is going to become the carboxylic acid. Okay, now here is it looking like vaguely normal. Okay, every carbon of the double bonds are gone. Okay, they are changed into something with a carbonyl on it. If it has 2 H's, you get CO2. If it has 1 H, you get carboxylic acids, and if you have 2 H or no H's, 2 carbons, you get a ketone. Those are the only 3 options that you can get with K-mineral. Okay? So notice that the number of carbons in your products should still match. Don't be adding extra carbons by accident. Okay? Keep that in mind. All right, so how about this one up here? Okay, we're cutting that one. Okay, so where am I cutting? Do you have this one? Oh, well, you can just write it on the back here. It's a good one. It should have been right there. Okay, so draw that structure out. Yeah, it's easy to draw, it sticks. And then cut it. So I got a string and I'm cutting it in 2 places. How many pieces am I going to get? String, and I'm cutting it in 2 places. How many pieces should I get? 3. Does that make sense? Okay, it should make sense. So I'm going to cut it here, and I'm going to cut it here. So start with each carbon in turn and just work through it. So the first carbon over here on the left, that piece of the double bond is going to give you what? CO2. Okay, then what is this carbon here going to give me? A carboxylic acid. Okay, that's this carbon here. And then I got a CH2, right? And then I have another carbon. Okay, and what is this carbon up here going to give me? This one right here. It's going to give me a what? It has how many R groups on it? 2. It's a di-substituted. 1, 2. So you get a ketone. Okay, that's the piece in the middle. What is on the right side of the green squiggle where we busted it? What are we going to get? It just has 1 R group, so what kind of compound? What functional group? Carboxylic acid. Happens to be acetic acid. Okay. Okay, we'll make it look nice. Look at that, isn't that nice and pretty? Okay. Notice the number of carbons matches. If you go 1, 2, 3, 4, 5, 6, 7. Over here you should have 1, 2, 3, 4, 5, 6, 7. Don't add extras. That's usually what people do is they add extras. Or lose. But what happens to that CO2? Probably evaporates. This, it bubbles out of solution. This will be soluble in water. And then this one is what you'd probably end up getting.
Do we have to write it pretty?
No, you don't have to write it pretty.
Okay.
You can write it however you want, as long as it's right. I don't care. I can figure it out. Okay, so now I'm going to ask you a different question, though. What is the alkene that would give these organic products after treatment with hot concentrated KMnO4? In other words, what did they start with to end up with those? So how do you do it? What do you think about? What you thinking? So what can you tell me about this carbon and this carbon? What?
The 2 R groups.
Right. And what are, remember, we're trying to come up with 1 compound. So what are those 2 carbons? They're the 2 carbons of the double bond. Right. Okay, so can you draw it? Even if you draw it funny. Okay, so like you might start like this, and this is going to be bonded to this, and I got 1, 2, 3, 1, 2, 3. Okay, again, the number of carbons should match. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Make sure that it matches. Okay, so here's what it looks like drawn nice. Because if it's multiple choice, you'll have to figure it out. Okay? Now it looks nice, but you're just sticking them together, Make sure you put a double bond between them. Okay, but you're sticking them together. Okay, we're going to do another one. Do you have another slide with it? Oh, maybe we do it after we do the ozone. All right, is ozone the next slide? Okay. Oh, no, we just have this. Okay. All right, so now you're going backwards. Can I get that to go away? It's like, you know, I'm so scared it's gonna. All right, here, let's try this. Hopefully it's still recording, right? Okay, what alkene will give the products below after oxidative cleavage with hot alkaline potassium permanganate? What does the word alkaline mean? Basic. Means it's basic. Okay? It's another word for basic. Yeah, so basically you're going to stick them together. We'll do what we just did with those compounds. Okay, so what carbons are the carbons of the double bond? What carbons end up coming from the double bond originally? This one and this one, right? So you're going to stick them together at that point. So if you even just went like that, that would get you there. Okay, make sure you have 1, 2, 3, 4 double bond. 1, 2, 3, 4, the double bond, and then the other two. This is acetone, by the way. Okay. Any questions? Okay, you're just going to take a little practice to be able to go backwards. Okay, ozonolysis. So who knows what ozone is? It's O3. Oxygen is O2. Ozone is an allotrope of oxygen. It also is a layer in the stratosphere that provides protection from radiation from the sun. You all know about our ozone layer, and you all know how we got a hole in it, don't you? Okay. It's a pale blue gas at STP. What's STP? Standard temperature and pressure. Remember that? Okay. It's highly corrosive and poisonous. Don't be breathing ozone. No ozone. Okay? Are you writing stuff down?
Yes.
Okay. O3. Okay. So we're talking about ozonolysis. So what is ozone going to do? What's lysis? Can you talk about that in biology? What are you doing when you're lysing something? Cutting it, you're breaking it. Okay, so we're going to do that, only we're going to use ozone to do it instead of potassium permanganate. There's just some minor differences. Okay, here's the Lewis structure of ozone. I should have asked you to draw it, shouldn't I? Okay, there has 2 Lewis structures. Okay, so notice that. That's how you go between them. Okay, there it is, pale blue. It's supposed to be pale blue. Okay, so both of the OO bonds in it are equivalent. They're both in between a double and a single. Okay, so we're going to break our molecule using ozone. And of course, we're going to break alkenes. Okay, got that right? All right, so here is a generic alkene, and we're going to add ozone to it. And what we're going to do first is it just adds the ozone across the double bond. So it looks like that. That is referred to as a molozonide. Okay, then that molecule actually rearranges to become an ozonide. Look at what happened. It opens and recloses. It's funky. We're not going to worry about it. That is your ozonide. And then you have to add one of 2 things, either zinc in water or dimethyl sulfide. Okay, either one will do the same thing and give you your carbonyl compounds. We are going to get aldehydes and ketones, no carboxylic acids. Okay, that was the permanganate. This one doesn't give you carboxylic acids. It gives you aldehydes or ketones. Okay, ready for example? Did you have to draw that down or what? All right, so here's the first one. Oh, and I wanted to mention about the alcohol. Sometimes they put it in and sometimes they don't. Typically, methanol or ethanol are your salts. You don't have to worry about it, but you might see it, and I don't want you to start adding OCH3. Okay. All right, so what are we going to do? We're going to break the molecule. Where? At the double bond. Okay. And you're going to basically put a carbonyl on the left carbon and a carbonyl on the right. It's even easier than the other one. Okay. Does anybody know what the compound on the right is called? Formaldehyde. You know anything about it? Yeah, it does. It used to be used to store biological specimens for many years. And then they went through, I think they did it after I was here even, upstairs. Well, it was up, biology used to be upstairs before they moved. And they went through and they transferred it all from formaldehyde to something else. I don't even know what they used. But formaldehyde is very water soluble. Okay, and so it'd be very easy to get that aldehyde and get rid of the formaldehyde from it. It would be very easy. Okay, notice that the groups on your carbon are still there. Okay, you still have that 6 carbon chain and a hydrogen. Okay, now what happens on the next one? What do we got to do? Cut it. Chomp it. Take your scissors. All right, so what do we get from the left side? Just redraw that and put a carbonyl. And what do we get from the right side? From this side, we get formaldehyde again. Look at that. You all are making aldehydes and ketones. All right, now how about the bottom one? What do you think is going to happen on the bottom one? Oh, let's switch colors. What? We're going to cut both of them. There's no preference for one or the other. So what do you get from this piece? From here, we get a CH2, and then we get a double bond O. We get formaldehyde. We only get CO2 when it's permanganate. That's what you got to keep straight. Yeah. I'm sorry. They're different. All right. What happened to this one? This carbon gives us an, you're right, an aldehyde. Then we have this, and we have this, and we have this, and then we have this carbon, and that gives us another aldehyde. And what do we get from this one? Acetone, a ketone. Oh, I guess I'm on the right thing. Here's the first piece, here's the second piece, and here's that last piece. Okay, both of these are super water soluble, so you can easily get that funky dialdehyde from that. Kind of a wild compound. Okay. Okie dokie. Now, I didn't mention anything about the second step. So I do want to mention that before we notice that here they use the dimethyl sulfide, here they use the zinc, and here they use the zinc. It doesn't matter. Okay? If I asked you for reagents, you could put either one. And you don't have to put the methanol, but you might see that in problems and book and stuff.
What is the percent? Like, why? 75 and 60?
Yeah, that's just what they got when they did the reaction. They got a 75% yield or a 60% yield. That's their isolated yield. I don't even have a number for this one. Sometimes they don't give them to me. And sometimes I make them up, and then I'm not going to go look it up. You don't have to know that. All right, so do this one. Is it too easy? Is that? It's not so hot up here today. It's hot up here last week. Today it's not so hot. 18? How did I get 18?
You clicked the button too fast.
You did.
I think there's actually like 19 buttons because like.
Yeah, but everybody wanted here. I counted and I counted 16, and then what's the one?
I want that too.
Who? Oh, that explains it. Right, gotta be fast in this class, let me tell you. All right, so we're breaking it here. So from the left side, I'm gonna get that. From the right side, I'm gonna get that. Okay, so to speak. Okie dokie. We getting it? That would be good because we're going to go backwards. Okay, so what alkene would give each set of carbonyl compounds upon ozonolysis? Now, you see this little arrow? This is referred to as a retrosynthetic analysis arrow. It means, what could this be made from? Okay, we're going to make both of them in one step. So, stick them together, kind of like we did the permanganate. Okay, so what are we going to do? This carbon and this carbon are special. What's special about them? They're going to make a double bond. Okay, and I do want to make you sure that you notice that the question asks, what alkene would give each set of carbonyl compounds upon ozonolysis? So please draw a compound that is an alkene. That is like a glue, okay? Yeah, I wasn't trying to be sneaky. I'll get a lot of alkanes for answers. Okay, do you see that this is one of these and this is the other one? You see where these two blue carbons are in there? Okay, because if you can do that, you can do all of them. All right, now what's the next one you think? Try to do it, and then I'll click the button. And you can draw them funky. You don't have to draw them like nice. Like I would take this and I go. Okay, 1, 2, 3, 4. 1, 2, 3, 4. And then I take that one and go like that. That's cool. That doesn't bother me. Okay. You might have to like think about it if it's a multiple choice question, what the compound is drawn out a little bit different, but But if I ask you to draw it, I don't care how you draw it. What?
I can draw it.
Yeah, right. Yeah. Okay. Okay, how about this one? What? You want me to go back? Why?
Can you show me that answer again?
Huh. I mean, I drew it up here too. Does it make sense? What is confounding you? Are you not liking the fact that I drew this one upside down and sideways? 1, 2, 3, 4, 5, 6.
I think
Oh, okay. Yeah, that'd be something to do too. With the number of carbons that are in the two compounds and the answer are the same number. Okay, the O's are gone, but the carbons are the same. Okay, all right, here's the next one. How did you do on this one? Still doing okay. All right, so this carbon and one of these. And then this carbon and this one. Doesn't matter which ones I put together. Well, I can't put this one and that one together, right? Because that's like you dead-ended yourself. This has to be in the middle. Agree? Is that kind of logical? This has to be in the middle. Doesn't matter what order I put them. But do you see that it's symmetrical? So it doesn't matter if I pick these two or if I pick those two. Okay. All right, so what'd you get? Okay, so these carbons, I'm going to mark them in here. Are there? See how it went together? Okay. Now, if you look at this double bond right there, did anybody draw it different? Okay. You cannot tell if the double bond was E or Z, cis or trans, using this method. Either answer would be correct. Okay, so if you flip that and you drew it this way, it would also be correct because you can't tell that from this reaction. Either one of those would be acceptable answer. Okay, that makes sense? That you can't tell that because once you chop it, you've lost the E or Z part. Okay, what if that was the only thing that you got? You only got one product, has two carbonyls. What would give that as a starting from the? What starting material would give that as the product? Ah, yep, a ring. Good job. All right, so how am I going to make the ring? What do you know? The carbons of the carbonyls are the carbons of the double bond. So this and this are going to be stuck together. Okay, how many carbons are in just the ring part? 5. Everybody get 5? 1, 2, 3, 4, 5. So I'm going to go like this. Start with this. Okay. What else is attached to this carbon? A methyl. Okay. And then we go to the next carbon. What's on this one? Methyl. This one. Nothing, honey. Okay. What about here? It just has an H. And you can draw it in, but you don't have to. I mean, it's inferred by the stick. Does that make sense? Don't just put the ends together. Okay. So when you break this, you should get that. And you can go backwards to help you, go backwards and forwards to help you figure out. Remember that the carbonyl carbons make up the carbons of the double bonds. So stick those together to make them holding hands. Okay? Okay, this was the last slide that I had. So this is synthesize each of the following from an alkene. So I want you to make sure that you have tried them by Monday. Okay, and I'll show you the answers. All right, y'all have a good weekend.